Not going to happen, right? I square any number, it's going to be positive. The most that could ever happen is you give me 0, but then I'm going to have 4. I'm trying to see if you can recognize just by looking at that that's not possible.
Well, yeah, because when you move that 4 over, you're going to eventually square root the -4.
That's right. That's right.
Number.
Yep. So there's two ways to look at this. You can look at it as, oh, if I move the 4 over, I'm going to get a negative, I'm going to need to square root it. Another way to look at it is, if I just look at that, that has to be positive or 0. If I add 4 to that, it's got to be bigger than 0. Right? There's no way that could equal 0. It's not possible to do it. I think it's good to see it both ways. Do you see it my second way?
Yeah.
Yeah? All right, so no solution. No real solution. All right, what about where the second derivative is undefined? -1 and 1 again, right? So we do have two places to look at. So I draw a number line. -1, 1. Split it up. Remember, these points do not live in my graph, right? But they are important points on the graph for sure. What should I get now?
-0 test points.
Test points?
So -2, 0, 2.
-2, -2, 0, 2. Where are those going? Where are they getting plugged in? Second derivative, right? Second derivative. So what is the second derivative at -2? What's the second derivative at 0? What's the second derivative at 2? Well, what can you tell me about the top? It's always positive, right? That's cubed, so I have to actually figure this out. What's -2 squared? 4 minus 1, 3 cubed is positive. So positive over positive is positive, right? What about 0? Positive on top? 0, that's -1 cubed. Negative times negative times negative is still negative. So this is going to be negative. And then if you plug in 2, you get positive.
How many of these are you going to test?
I can pretty much only ask you one, I think, right? It's a big chunk of the test right here, if I ask you one. These are so time consuming, but there's just so much, there's so much in here, you know, that
You're getting where it's just the whole test is just one problem.
not just this problem, no. Yeah. All right, keep going here. This second derivative being positive here tells us the original function is concave up. The second derivative being negative here tells us the original function here is concave down. And the second derivative being positive here tells us the original function is concave up here. Right? Do we have inflection points?
Well,
Oh, no.
no, because they're not in the domain.
They're not in the domain. You have to have a point in the domain of the function where we see. So like we've been looking at inflection points where the smile and the frown come together. But see, this smile and this frown aren't going to come together because there's going to be an asymptote right there. So they're never going to come and have a point where they connect. So we have no inflection points. But they're not asking us for inflection points. They just want us to graph it, right? So at this point, I'm ready to put together all the information and draw my picture. So what I'll do is, like I did before, with that sine function, that sine x plus cosine x, I'm going to start with a little grid up at the top of the page, and then I'll draw below it. So my number line is going to go like this. I better give myself a little more room. I like to start with the critical numbers. So that's, we had some pictures that we did already, some grids that we did. What were the important points off those grids? So for first derivative, it was, what, 0 and negative 1 and 1. Oops. All right. So I've got that so far. Were there any other critical numbers off of like the second derivative? It was negative 1 and 1 again, wasn't it? Okay, yes, we did the testing, but as far as the critical numbers, these were them, right? So you want to be sure, don't put your test points in here. We good? All right, well, let me try and come up with my 3 rows here. I have, what did I say put on the bottom row? F prime, then double prime, and then F. So tell me about the first derivative as I walk across here. First derivative. Function's going to be doing what over here? Up? Okay, so function going up, then up still? Down? Down? Okay, tell me about the concavity. Concave up? Up? Down, down. And now put those 2 pieces of information together vertically to figure out which side of the smile and frown you're on. So right side of the smile, right side of the smile again. Right side, frown, right side, frown. You got it? Now below this is my picture. Here's my y-axis. I have this important point 1, negative 1. And I'm going to start bringing everything together, okay? All the information. Back from here, in the beginning of the problem, I knew I had an x-intercept right at 0, 0. I knew I had vertical asymptotes, which are not part of my graph, right? But there are these vertical barriers I can't cross. I have a horizontal asymptote, don't I? At 2. And that's out here, which again is not part of my graph, but it tells me what's happening at the ends, doesn't it? Is there any other information I haven't put on here? I think I've got it all, right? Help me draw this. To the left of negative 1, I've got to look like this. But I have to approach that, and this barrier is going to force me to go up or down. I have to go up because I have to look like that, right? So it's going to have to look like this and then like that. Do you agree? When I get here, hold on a second. Something ain't right there.
Because our got max is 0.
Yeah, hold on. Okay. I'm glad someone caught this. Go back here. This was supposed from negative 1 to 1, it was concave down. And then up. I was just going off of whatever y'all were saying, whoever said it. Right? You should have it written down. We did all the work, right? Go back and check the second derivative. Did we have up to negative 1, then down to 1, and then up from 1 on? Concave? Yes? That changes some things, because look at our picture here. This should actually, right? We got to redo all that. This should be here, this should be here, and this should be here. We all get that? Why'd y'all let me get that far with it? It was on a different page? All right, so let's see. Between negative 1 and 1, I have to draw this, right? but I have to get to this point. So it's got to look like this. The asymptote forces me down, doesn't it? From here to here, I have to look like this, but I also have to be at this point. So it's got to look like the other side, like this. Then over here, I've got to look like this, but I've got to approach this, and my vertical is here, which forces me to go up. So it's going to look like that. It was 2x squared over x squared minus 1, right? Was the original function. Take this interval off. Is it symmetric to the y-axis?
Yeah.
43 minutes. That only took me about, what, 30 seconds to type in? Yeah, let's see if we can get one more in.
I had a quick question.
Yes.
I've seen her sketches before.
Yes.
Would it use limits to determine whether it was going to like positive thing or negative thing?
Uh-huh.
At the asymptote?
Yes.
How are we avoiding that?
Mm-hmm. What about it?
How are we avoiding doing the limit of the asymptote to figure out where it's going, if it's going to negative infinity or positive infinity?
We did when we did the horizontal, we did let x go to infinity, and we used L'Hopital.
Yeah.
Yeah? And we got 2,
Okay.
right? So we did do that.
I was like debating, I looked over like, I was like, I probably won't have it.
Oh, the charge.
Yeah, it's expecting normal.
Is that okay? I mean, am I addressing your question?
Because I barely remember whenever I did it before.
Uh-huh.
But I remember using limits to like whatever the asymptote, we would go limit x to the asymptote, and then that way we could figure out if it was negative infinity or positive infinity. Because I remember doing it with the infinities for the horizontal asymptote.
Are you talking about the slant asymptote?
No.
No?
'Cause I've never heard of slants.
Okay. Let us do another one and see if it comes into play again. You know, if you still have the same question.
Slant on the handicap. Asymptotes are the same, just different name.
No, the slants are different. Slant asymptotes are different. It's, huh?
Different than oblique asymptotes.
Oh, no, they're the same. Yeah.
Yeah.
Well, we just last,
And, you know, as long as I've been doing math, I mean, I very rarely have ever, like later on, have ever needed that.
yeah.
Yeah. All right, let's take a look at this one. All right, there it is. So let's go through this. Domain. Any domain issues? Well, you can plug anything you want in for x, right? So no worries there? No domain? Yes.
I have a question for the test. I
Uh-huh.
remember back in 1414 you let us use that like
Set of steps. Yes, you can, I mean, those steps I'd probably be okay with you using.
We put them out.
Yeah, like I'd probably provide those for you. But see, the thing is, look at what it says at the very top. Suggested steps. Like it's not necessarily absolute, you have to do this, 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 this. That's just if you want to get a feel for what's happening, usually this is enough for us to be able to sketch it. It's in no way like the accepted way of doing it.
it's just like because I'm not gonna remember it.
Yeah. All right, so what's a domain? are real numbers, right? So we can say negative infinity to infinity. So we should have graph everywhere, right? We're going to not have any vertical asymptotes or anything like that. 2, do we have any x-intercepts? So we set the function equal to 0, right? And the left side's already factored out, isn't it? I mean, it's 2 things being multiplied. So just set them each equal to 0. When does, well, this is obvious, right? X is 0 when x is 0. How about e to the x? Is e to the x ever 0?
No. Oh, yeah. Once. Yes.
What does e to the x look like? If I graph it as a function. Look like this? You have a horizontal. So does it ever equal 0? No, it never equals 0. It's not possible for that to ever equal 0. So no solution there? So we only have 1. Now for those of you who like to do things more algebraically, I can kill off e by doing natural log. But natural log of 0 is undefined. So you wouldn't be able to get an answer here, like because the left side turns into x. I like to look at the graph though. I think it's a little easier to understand that way. All right, so we have one x-intercept, right? So if I'm drawing my picture again, it's going to look, so far it looks exactly like the other one did at 0, right? They both have that point.
So when you multiply e to the x by x, it gets rid of that horizontal asymptote.
When you do what?
When you multiply e to the x by
Times.
Because there's a horizontal asymptote on e to the x, but there's not.
There's not one there. It's going to do something to it. It's going to do something to it. If you think about it this way, here's e to the x, right? If I put an a out here, do you remember what a number in front of a function did? There's like a dilation or something here. If a is bigger than 1, it actually like stretches it out this way. If a is less than 1, then it makes it compress down. If a is negative, it flips it over. Well, guess what? We have an a that keeps changing. So as you move along the function, you're dilating one way, stretching a different way, flipping it. There's a lot of things happening. I'll show you something that's really cool at the end, all right? Just let me get through this. So at 0, it's killing it off, right? How about a y-intercept? Plug 0 in, and you get 0.
Because e to the 0 is 1.
That's right. So you have f of 0, which is 0, e to the 0, which is 0 times 1, which is 0. Which is the same as the x-intercept. 3, symmetry. Is this one symmetric? Is f of x equal to net f of negative x? Well, is x e to the x equal to negative x e to the negative x? No, not at all. Just plug 1 in, right? Just plug 1 in for x. Just to give yourself an example, it doesn't work. Is e to the 1 equal to negative e to the negative 1? No. So that's no go. No symmetry, right? No symmetry? Not over the y-axis. What else? Asymptotes. So what we do for asymptotes is I take the limit as x goes to infinity of x e to the x, and then I also need to let limit as x goes to infinity, negative infinity, of x e to the x. So let's talk about the first one.
Vertical. Oh wait, no, because
I'll get to those. Yeah, this is to check for our horizontal asymptotes. Why am I not checking for vertical?
because the domain's all real.
Yeah, you don't have any division here, right? So x goes to infinity. What happens here? This becomes infinite times e to the infinity is infinity. This is infinity times infinity, which is infinite, right? That we can tell. Infinity times infinity, that we can say is infinity. As opposed to the next one. if x is going to negative infinity, do you agree this is negative infinity times, what's e to the negative infinity? E to the negative infinity, right? Something like this, which is really negative infinity times 1 over e to the positive infinity. 1 over a number that gets huge goes to 0. So what we have is negative infinity times 0, and that's an indeterminate form, which means we need to somehow figure out what the hell that's doing, right? And remember how to determine when you have 0 and infinity multiplied, what the common trick was? Drop 1 down. Good. You drop 1 down. So let's see if we can drop 1 down. So I'm trying to do, so I'm question mark here, right? I don't know what the hell that is. Limit x goes to negative infinity. I'm going to drop the e down. Now, the reason I'm dropping the e down is because it's easy for me to write e to the negative x. If I drop the x down, it's going to become what on the bottom? X to negative 1 or 1 over x. Okay, that derivative is not as clean as the derivatives here are going to be, right? Let's just double check real quick that we still have what we need for L'Hopital. What does the top go to? Negative infinity here, negative infinity up top. Now watch how things changed. Negative here, negative negative is positive, right? So e to the infinity is headed to infinity. Now you have infinity over infinity instead of 0 times infinity. Do y'all see the difference? So now I can use L'Hopital. L'Hopital. Oh, no. Derivative of the top. Derivative of the bottom. Same thing, but with a negative 1 out there, right? Because you have to take derivative of what's up here. That's okay, though, because when I let x go to infinity now, or negative infinity, what happens? This thing goes to positive infinity, e to the positive infinity, blows up, fixed number over something that's blowing up, it's going to go to 0. So this goes to 0. Whew. All right, so this means that when we draw our graph, out the right side, where's it headed? At the right side, it's headed up to infinity, but out the left side, it's headed to 0. So it's going to look like, you know, I have like a horizontal asymptote over here somewhere on the x-axis. Then over here, the function is going to go up there. I'm still going to have to put it all together, but that's what it's going to look like.
How do you have the horizontal asymptote at 0, but equal to at 0?
You can be equal to your horizontal asymptote. Your horizontal asymptote only tells you where your function is headed. That's one of the misconceptions from college algebra, and I'm pretty big on this in my college algebra classes. I don't know if you've ever seen this before, but like when you're graphing a rational function, you find your vertical asymptotes, and then you find your horizontal asymptote. And I see people do this all the time, and they draw their horizontal asymptote all the way across like this. And that is like a big no-no in my classes, because your horizontal asymptote is not a barrier. It doesn't stop your function from being that value. It just tells you where your function's headed towards at the end. So anything can happen in here. It's just what's happening out there. Not only that, but you could have, does that kind of make sense? Okay, not only that, I could have a horizontal asymptote like this of 0, and I could have a function go like this. In oscillating and going above it and below it and through it over and over and over, and every time it's getting smaller and smaller and smaller, that would still be approaching 0, and we'd still have a horizontal asymptote of 0. Okay? Okay, we are in trouble with time here. All right, first derivative. I think the derivative's not going to be too bad. Would you agree? Little product rule there. E to the x plus x e to the x. That's the first derivative. You want to take derivative again? E to the x plus, and then that's going to be e to the x plus x e to the x again. Which is really just 2 e to the x plus x e to the x. So because of time constraints, I'm going to assume you could get those on your own. If you can't, go back, ask me questions later. All right, so let's figure out where our first derivative is 0. Where's our first derivative 0? Where's the first derivative undefined? So how about where it's 0? I have to set e to the x plus x e to the x equal to 0. Can you do anything with that? You can factor an e to the x out. Good. What would you be left with?
Oh,
1 plus x, right? Set each of those equal to 0. Can e to the x ever equal 0? No. Can 1 plus x ever equal 0? Yes, if x is negative 1. So for this one, x is negative 1 is going to be a critical number. Is your derivative ever undefined? No, because this is well-defined, that's well-defined, so no problems there. It's going a little faster than the other one was, right? With derivatives. What am I going to do now? Number line. Number line. What number am I going to put on that number line? Negative 1. Oh, good. I'm only going to have to test 2 points. 0. Okay, I like that. Negative 2. Plugging those into the derivative. I actually think we should plug it into this one. I like this version of the derivative that was factored. It's easier for me to tell what's going to happen here. Because e to any power is what? Positive, right? So I don't really care about that. It's just what is 1 plus x. So if I plug in negative 2, that's going to turn out to be negative, isn't it? So I'm starting to work a little faster now because we've been through this a little bit. Going down over here, right? My function's going down over there because my derivative was negative. Over here, I plug in 0 into this. My derivative would be positive, wouldn't it? Which means my function's going up over here. Do I have a local maximum? No maximum. Do I have a local minimum? Yes. Well, is negative 1 allowed to be in there? Is negative 1 in the domain of my function? Remember, our domain was all real numbers, wasn't it? So yeah, that's a local max. I mean, that's a local minimum. Right? That should be a lowest point locally on my graph. But they're not asking for that. I'm just pointing it out that it is a local minimum. Questions, comments, concerns, gripes up to this point? What's next?
Now we can second derivative.
Second derivative, same story, right? So second derivative equal to 0. All right, where is the second derivative undefined? So here is my second derivative, right? I need to set it equal to 0. What can we do to that second derivative when we set it to 0? Take out that e to the x again, right? This time you'll have 2 plus x. What's the solution to this? Negative 2. Am I moving too fast, or are you all keeping up with this? We're good? All right. So now where's the second derivative undefined? Nowhere, right? So no issues. So I'm going to go through this again. But I have negative 2 instead of negative 1, right? 2 test points, negative 3 and like 0 again. What are we going to get? Negative, so what should I put here? If I'm going to kind of follow the trend of what I've been doing here, what should I put here? Concave down and then concave up. All right, we're getting close on this one. I'm ready to go number line. Oh, inflection point? We do have an inflection point, negative 2. All right, here comes my drawing. which I start with up here, number line, I had -1 and -2. Those were the 2 points that were kind of vital in my picture, weren't they? I create my 3 rows from this. And I'm going to try and go off my memory here. This time, check, all right? I think it's down, down, up. Yep. And then down, up, up. And down a frown is this. Down a smile is this. Go up a smile, this. Yeah, we were in calculus today and we were talking about going down a frown and up a smile. Yeah, it sounds pretty complicated. All right, so here we go. Put -2 down here. Put -1 here. And then let's go pick some points that were on our graph over here. Anything that we knew, like anything that we knew for sure. 0, right? That point lives on our graph. Wonderful. We don't have any other points, do we? We know that we do have a horizontal asymptote down here, don't we? And we know that our graph does head up in this direction, right? Somewhere over here? From somewhere, right? From somewhere over here, it heads up. Okay, so wouldn't it be nice if I had a couple of more points? And the most likely candidates for values for us to plug in would be what? -1 and 2. So let's just figure out where these points are on our graph. And for that, we're going to have to plug them in. What's f of -1? What's f of -2? So that means I need to go -1 e to the -1, then -2 e to the -2. And you're going to have to use your calculator for that. So then the top one, negative, what are you getting here? -0.367. Anyone else got that? Anyone else trying? Yes, you got the same? Okay. And then how about the next one? Should be even smaller.
The -0.27.
0.27?
Yeah.
271.
Okay. What's going to be important to us is that they're both negative numbers, and then which one is above and below the other one. So at -1, this point is down here, let's say here, right? Let's just say it's right there. Then at -2, we should be up or down, a little bit above? So something like that. So if that's like -0.27, this is like -0.36. That should be enough. So let's see. To the left of -2, it's got to look like that, right? It's got to flatten out towards that. So I've got to make this look right. Let me see. There we go. That okay with you? And then from here to here, it's got to look like this. Oh, there we go. Oh, shit. Trying to get a good inflection point there. And then from here to here, well, from here to forever, right? It's got to look like that. So I'm just going to go like this. Like that. And that is the graph of x e to the x. And we will verify. There it is. So from the calculator, I mean, from the computer's picture, what you can't really tell is where your inflection point is. I mean, it's kind of hard to tell what that is. I mean, maybe you were like, nah, I can see that, man. I don't know what you're talking about. You know, if I zoom in, maybe you can see it. I don't know. If I zoom out far enough, though, you ain't giving me no inflection point for sure, right? But the calculus, it's very obvious where these things are happening, right? Local minimum right here. Actually, is that a local minimum? That's a global minimum, isn't it? It's a global minimum. It's the lowest point on the graph. Right. We said local, though, right? We said local. So here, wanted to graph something else here. We're almost out of time. X. Yeah, it's not a good one. Let me show you this. This is one of my favorite examples. If you take a graph like this, we're done with this problem, yes? Okay. So if you take a problem like this, sine x over x, like there's a function, let's graph it, all right? If I were to take, you know, let's make it squared there. It's 1 if x is going to 0 in a limit, right? I'm glad you recognize that. But, so if I rewrite this, this is 1 over x squared sine x. Do you agree? Okay, so we know that from pre-cal that the number in front of the sine function is the amplitude. Right? So what's happening here is this right here is now representative of our amplitude. As x gets bigger, the amplitude does what? Gets smaller. As x approaches 0, the amplitude gets bigger, doesn't it? If this number gets small, 1 over that gets big. Let's take a look at what this is going to be. This is going to be a really cool looking function. Sine x over x squared. I'm zoomed in. Okay, so as you can see here, it is oscillating. You see it there? It's hard to see it. What I'll do is I will change the period. There, that gives you a better idea of what's going on there. You see it? So it's a sine curve, but it's being what we call dampened. All right, we're dampening the sine curve. So like if you imagine like dropping a ball, and it's goes up, down, but each time it doesn't come up as high, and eventually This is a better model of that behavior than a sine curve would be, because sine, it comes all the way back up, all the way back down. You want that to taper off, don't you? Like to fit like what's happening in the real world. But what I want to show you that I thought was cool about this is that this amplitude function, if I graph just 1 over x squared, watch. And I'm also going to graph -1. So I just graphed 1 over x squared and -1 over x squared. And do you see what that does? It gives you a visual representation of this funneling effect that you're having. You're starting with the regular sine curve, and you're trying to force it between 1 over x squared and its reflection over the x-axis. It's kind of cool, right? All right, well, where do you even begin on this homework assignment? I mean, if I assign you 15 problems, it's going to take you till 3 weeks from now, right? I mean, this is a lot of work. So what I would do is let's just be realistic about this. I think you should be able to do a simple problem. So I think you should be able to do, off of page 230, something easy like number 1. But then I also think you should be able to handle a rational function, which would be something like number 13 or maybe 16. But I also think you should at least have some exposure to something nasty, like 17 or 24. So this is like different groups here of level of difficulty here. Like 1 is the most basic you could do, and 13 or 16 are kind of medium. And then if you just want to really kind of test your abilities, you could go out and try something like 35. So my approach, if I were you, would be start with the first one. If that one is okay, move on to like 13. If you go, oh crap, wait, you know what, 13 is hard, maybe go try a few more. But realize when you sit down to do each one of these problems, you're looking at anywhere from 15 minutes to an hour to do the problem. All right, so have fun, I guess. We'll pick up with more of this next class, all right? I think I have 2 days dedicated to graphing, so we'll do more graphing next class.
We had 2 days dedicated to